Consider a metal conductor. Current in a conductor is due to the valence electrons in it. The valence electrons are not bound to any particular atom and are free to move about within the volume of the conductor. These electrons are called the conduction electrons. Rest of the conductor is made of relatively heavy positive atoms that are referred to as the lattice. Let us consider a conductor that is not connected to any battery or to a cell. Hence, there isn't any electric field. The free electrons move at random, collide within themselves and with the ions in the lattice. The radius of an electron is very small as compared to that of an atom. Hence, the collisions between conduction electrons and other electrons are neglected. As the conduction electrons move at random, they have different velocities in different directions. Let the velocities of the free electrons at any given instant be u1, u2, and so on up to un for n number of electrons. As the directions of the velocities are random, the vector sum of the velocities of all the electrons is equal to 0. Hence, the average velocity of all the electrons at the instant u is equal to 0. Let this be equation 1. The motion of these free electrons is called thermal motion, as the motion of these electrons depend on their average kinetic energy. Average kinetic energy of the electrons depends on the temperature of the conductor. Since the average velocity of the conduction electrons at any instant is 0, there is no net transport of electric charge. Thus, there is no net electric current through the conductor. Now let us consider a conductor connected to a source of electromotive force, such as a cell or a battery. When the conductor is connected to an external source, an electric field is applied across the conductor. Due to the electric field, the free electrons are accelerated in the direction opposite to that of the field. The magnitude of the electric charge on an electron is E. If E is the magnitude of the applied electric field strength, the force on the electron F is equal to E into E. If m is the mass of the electron, then the acceleration of the electron A is equal to the ratio F to m, which is equal to E into E by m. Let this be equation 2. Due to the acceleration, the free electrons gain velocity and hence kinetic energy. With the acquired kinetic energy, the free electrons collide with the atoms within the conductor. During such collisions, the electrons give up their energy to the atoms. Hence, their velocity decreases. Immediately after the collision, the free electrons are accelerated due to the applied electric field. This acceleration gain increases the velocity and thus the kinetic energy of the electrons. The electrons again collide and lose their kinetic energy. Due to these repeated collisions, the average acceleration of the electrons is reduced to 0. Hence, the average velocity of the free electrons is constant and is directed opposite to the direction of the applied electric field. The average velocity gained by the free electrons in a conductor when subjected to an electric field is called the drift velocity. Let us find an expression for the drift velocity of the conduction electrons in a conductor when subjected to an electric field. Earlier, we considered the velocities of n number of conduction electrons at any given instant to be u1, u2, so on till un. Now, when the electrons are subjected to the electric field, let their velocities be v1, v2, so on till vn. Here, v1 is equal to u1 plus a into tau 1, where tau 1 is the time between two successive collisions of the first electron. Similarly, v2 is equal to u2 plus a into tau 2, where tau 2 is the time between two successive collisions of the second electron. So on till vn is equal to un plus a into tau n. The average velocity of all the free electrons is equal to the drift velocity Vd. Hence, Vd is equal to V1 plus V2 plus so on plus Vn divided by n. Substituting the expressions for V1, V2, so on till Vn in the expression for Vd and simplifying, we get Vd is equal to u plus a into tau. This average time elapsed between two successive collisions of a conduction electron is called the relaxation time. It is of the order of 10 power minus 14 second. This implies that an electron is free from any collision for the duration of 10 power minus 14 second and is relaxed. The mean distance travelled by the electron during the relaxation time is called the mean free path. Let L be the mean free path of the electron. Then we get L is equal to drift velocity Vd into relaxation time tau. Hence, we get Vd is equal to L by tau. Let this be equation 3. We also get L using the equation of motion S is equal to ut plus half at square in kinematics, where S is the displacement, u is the initial velocity, a is the acceleration, and t is the time. From this equation of motion, we get L is equal to half a into tau square, where a is the acceleration of the electron. Substituting the value of the acceleration from equation 2 and simplifying, we get L is equal to half e into e by m into tau square. Let this be equation 4. Substituting the value of L from equation 4 in equation 3 and simplifying, we get Vd is equal to half e into e by m into tau. Let this be equation 5. From equation 5, it is clear that the drift velocity of the free electrons is proportional to the electric field strength E and the relaxation time tau. Equation 5 can be further simplified to get Vd is equal to k into E, where k is a constant equal to E tau by 2m. Let this be equation 6. The constant k depends on the material of the conductor and its temperature. Let us now find the relation between drift velocity and current density. We know that the magnitude of the current density denoted by J, is defined as current per unit area considered normal to the current in a conductor. Consider a cylindrical conductor whose cross-sectional area is A. Let the conductor be connected to an electric source. Let E be the electric field due to the source. If Vd is the drift velocity of the conduction electrons in the conductor, then the net distance travelled by the free electrons in the conductor during the time interval delta t is equal to Vd delta t. The volume of the portion of the conductor through which the free electrons travel during time delta t is equal to A Vd delta t. Let n be the number of free electrons per unit volume of the conductor. Then the number of free electrons within the volume considered is equal to n A Vd delta t. All these free electrons cross the area in time delta t. Hence, the charge crossing the area A in time delta t is given by delta Q is equal to NA Vd delta TE. Let this be equation 7. From equation 7, we get current through the conductor I is equal to delta Q by delta T, which is equal to NA VDE. Hence, the magnitude of the current density, J, which is equal to I by A, can now be written as equal to NVDE. Let this be equation 8. Substituting the value of Vd from equation 5 in equation 8 and simplifying, we get the magnitude of current density, J is equal to Ne square tau by 2m into E. The magnitude of current density, J, is also written as equal to sigma into E, where sigma is a constant called electrical conductivity of the conductor, which depends on the nature of the material of the conductor and its temperature. Thus, sigma is equal to Ne square tau by 2m. Let this be equation 9. The reciprocal of conductivity is called the resistivity of the conductor. It is denoted by the Greek alphabet ρ. From equation 9, resistivity ρ is equal to 2m by Ne square tau. Let this be equation 10. For a given material, n remains constant. The mass m and charge E of an electron are also constants. Hence, from the equation 10, it is clear that when the value of tau decreases, ρ increases. This implies that as the relaxation time decreases, number of collisions of free electrons increases. The collision of the free electrons with the atoms of the conductor restricts their flow, and this causes resistivity of the conductor. Similar to resistivity, another important property of conductors is mobility. Mobility is denoted by mu and is defined as the magnitude of drift velocity per unit electric field. Thus, mu is equal to Vd by E. Substituting the value of Vd from equation 5 and simplifying, we get mu is equal to E tau by m. Its unit in SI system is meter square per volt second. A potentiometer is a device used to compare the EMF of any two cells, to measure the internal resistance of a cell and also to measure the potential difference across a resistor in a circuit. We generally use a voltmeter to measure the potential difference across a resistor in a circuit. When the voltmeter is connected across a resistor in a circuit, it draws a part of the current in the circuit, altering the overall potential difference that is to be measured across the given resistor. This alteration leads to an error in the measured value of the potential difference across the given resistor. Thus, the voltmeter is not an ideal device to measure potential difference. An ideal voltmeter should have an infinite resistance. As it is not practically possible to have an ideal voltmeter, we prefer to use another device called the stretched wire potentiometer 2-voltmeter, which measures the potential difference across a resistor without drawing any current from the given circuit. We refer to the stretched wire potentiometer as a potentiometer in our context. To understand the principle of a potentiometer, we take a simple circuit where two cells with EMF, E1 and E2 are connected in a loop such that their positive terminals are joined and negative terminals are joined by connecting wires. A galvanometer G is connected in series in the circuit as shown. If the value of E1 is greater than that of E2, the net EMF is E1 minus E2, and hence the current in the loop is in the direction of the current due to E1. This can be observed by the deflection of the galvanometer needle in a direction. In case the value of E1 is less than that of E2, the net EMF is E2 minus E1, and hence the current in the circuit is in the direction of the current due to E2. Now, the deflection of the galvanometer needle is opposite to that in the earlier case. In case the value of E1 is equal to that of E2, then the net EMF is 0, and hence the current in the circuit is 0. This can be confirmed by the zero deflection of the galvanometer needle. In this situation, the potential at the negative terminals of both cells is equal. Also, the potential at the positive terminals of both cells is equal. Hence, the current in the circuit is 0 and the circuit is called a balanced circuit. Now let us learn about the potentiometer. A potentiometer consists of a long wire of about 10 meters in length, with a uniform cross-sectional area fixed to a wooden board. This is usually done with separate pieces of wire of 1 meter each, fixed parallel to each other to the board, with endpoints connected by copper strips so that the combination acts as a single stretched wire. The endpoints of the wire, say A and B, are connected to a primary circuit consisting of a battery, B, a plug key, K, and a rheostat, RH. Here is the circuit diagram of the circuit we have just described. The end A of the potentiometer wire is connected to the positive terminal of the battery. The end B is connected to the rheostat. When the key is pressed, let I be the constant current in the potentiometer wire along A to B. Thus, the potential gradually decreases from A to B. Let V0 be the potential drop across AB set up by the circuit. According to Ohm's law, the potential drop V0 is equal to I into R, where R is the resistance of the wire. We know that the resistance of the wire R is equal to rho L by A, where rho is the resistivity of the wire, L is the length of the wire, and A is the cross-section of the wire. Thus, the potential drop V0 is equal to I into rho L by A. Here, I is constant as already discussed. The resistivity of the material of the wire rho is constant. As the wire is of uniform thickness, the area of cross-section of the wire A is constant. Hence, the potential drop across any segment of the wire is proportional to the length of the segment. Thus, the ratio V0 to L is constant and is referred to as potential drop per unit length, phi, of the potentiometer, and is measured in volt per meter. Hence, we have V0 is equal to phi L. Let this be equation 1. If we need to measure the potential difference across a resistance in a circuit, we connect endpoints P and Q of the resistance to the primary circuit. Point P of the resistor is connected to point A of the primary circuit. As the connecting wire does not have any resistance, the potential at point P is the same as that at point A. Point Q of the resistor is connected to the potentiometer wire through a galvanometer G and jockey J. Thus, points Q of the resistor and J on the potentiometer wire are at a lower potential compared to the potential at point P or A. If there is a potential difference between points Q and J, there will be a current passing through the galvanometer. Contact is made on the potentiometer wire using the jockey, which is pressed at various points on the potentiometer wire. In this process of making contact at various points on the wire, we come across a point S on it, such that the potential at that point is the same as the potential at point Q. Hence, the circuit comprising points A, S, Q, and P is in a balanced state and the current in the galvanometer is 0. This circuit is also referred to as a secondary circuit. If L is the length of the potentiometer wire between points A and S, and V is the potential drop across the resistor, then the potential drop across AS is also V. The length L is referred to as the balancing length of the potentiometer wire. The ratio V to L is phi, and hence V is equal to phi L. Let this be equation 2. Dividing equation 2 by equation 1 and simplifying, we get V is equal to V0 into L by L. Let this be equation 3. To find the value of V, we need to know the value of V0. To find the value of V0, the resistor in the secondary circuit can be replaced by a cell whose EMF E0 is known. Then, contact is made using the jockey at different points on potentiometer wire till a balancing length L0 is obtained. Note that there is no current passing through the cell when the circuit is balanced. Hence, the EMF of the cell is equal to the potential difference across its terminals. In this case, we get E0 is equal to phi into L0. Let this be equation 4. Dividing equation 1 by equation 4 and simplifying, we get V0 is equal to E0 into L by L0. Let this be equation 5. This process of finding V0 is called calibration of the potentiometer. Substituting equation 5 in 3 and simplifying, we get V is equal to E0 into L by L0. Let this be equation 6. To compare the EMF of two cells with EMF as E1 and E2, they are connected in a secondary circuit separately, one after the other, and the corresponding balancing length of the potentiometer wire for each cell is found. Let L1 be the balancing length for the cell of EMF E1, and L2 be the balancing length for the cell of EMF E2. Then, we get E1 is equal to phi L1 and E2 is equal to phi L2. Thus, the ratio E1 to E2 is equal to the ratio L1 to L2. Let this be equation 7. This equation shows the comparison of the EMF of the two given cells. If both cells are to be connected at the same time, we use a two-way key in the secondary circuit for convenience as shown. If key K1 is pressed, the cell with EMF E1 is connected in the secondary circuit and the balancing length L1 is obtained. If key K2 is pressed, the cell with EMF E2 is connected in the secondary circuit and the balancing length L2 is obtained. Now, let us learn to find the internal resistance of a given cell using a potentiometer. The arrangement to measure the internal resistance of a cell using a potentiometer is shown. In this case, a cell of EMF E and internal resistance R is connected across points P and Q in the secondary circuit. An external known resistance R through a resistance box is connected to the cell via a key K' across points P and Q. Here is the circuit diagram for the arrangement. Initially, the key K' is open. This implies that the resistance R is not included in the secondary circuit. This implies that the potential difference across the cell in the secondary circuit is equal to its EMF. Now, the jockey is pressed at various points on the potentiometer wire to find the balancing length. If L is the balancing length obtained when K' is open, we get E is equal to phi into L. Let this be equation 8. When K' is pressed, the resistance R is included in the secondary circuit. The current through the cell I is equal to E by R plus R. Let this be equation 9. Then the potential difference across points P and Q, which is the terminal voltage of the cell, VPQ, is Vp minus Vq is equal to I into R. This is in keeping with Ohm's law. Let this be equation 10. Substituting the expression for I from equation 9 in equation 10 and simplifying, we get VPQ is equal to E by R plus R into R. Let this be equation 11. In this situation, the current from the cell in the secondary circuit does not pass through the primary circuit, as points A and P are at the same potential. Contact is made on the potentiometer wire using the jockey, which is pressed at various points on the wire till we get a balancing length L dash, where the potential drop across the length of the wire is equal to the terminal voltage of the cell. Thus, we have VPQ is equal to phi into L dash. Let this be equation 12. From equations 11 and 12, we get E by R plus R into R is equal to phi L dash. Let this be equation 13. Dividing equation 8 by equation 13 and simplifying, we get the internal resistance of the cell, R is equal to R into L minus L dash by L dash.